So today we'll continue our discussion on EDFAs. Right, so we'll look at how we model the propagation of the pump and signal waves as it travels through this erbium-doped fiber. So again, right. So imagine the core is doped with some concentration of erbium ions. So this cannot be some concentration of right, and basically we have some kind of pump mode and signal mode, right? So typically these would be single mode fibers, so the mode would look like a Gaussian, right? So the LP01 mode. So you have the pump mode, signal mode, right? And they are propagating through the fiber. The pump causes the population inversion, right? It pumps atoms from this first level, ground state, to this excited third level, right? So this is the pump frequency. And then the atom quickly, erbium relaxes to this intermediate level, and then the amplification happens at the signal frequency. Right, so at any distance z along the fiber, right? So there will be some atoms, some erbium atoms which are in the ground state, and some of them in this excited 2 state, right? We say that the lifetime of this third level is so short that as soon as it goes to 3, it immediately relaxes to 2. So there are no atoms in 3, right? So only there are atoms in 1 and 2. Okay? So, and in general, because the pump and signal mode have some intensity profile, right, with the radial distance. So this atomic distribution will also, in general, depend on the radial distance, and also, of course, the propagation. Right, so the sum of these two is the total erbium ion concentration. So, in general, this could also be a function of radial distance, right? If we dope according to some profile, but mostly, typically, we just dope it uniformly. So this I0 is a constant; it doesn't depend on radial distance. It's just a uniform doping across the board. So then now we can write the rate of change of the population in these two levels, right? So the rate of change of the atomic density in level 1, right? So the population is decreasing due to pump absorption. Right? So this we wrote down last time, right? So it's proportional to the absorption cross section at the pump wavelength. Then pump intensity divided by the photon energy. This gives me the photon flux. Right? Number of photons crossing per unit area per unit time across the pipe times time. So this is the absorption rate due to the pump, right? The atom goes from 1 to 3. Similarly, there could be an absorption due to the signal photon, right? So the atom could absorb a signal photon and go from 1 to 2. So that would be dependent on the absorption cross section at the signal wavelength and the signal intensity. Right, so this is from 1 to 2. And of course, there could be stimulated emission, right, which is what gives me gain from 2 to 1. So that is the emission process. Times N2, right, because it's going from 2 to 1. And so that's why it's a plus sign, because the atomic population 1 is increasing due to the stimulated emission. Okay, so this emission cross section we can write as the absorption cross section times this factor eta s. So the ratio of the emission to the absorption. So this is stimulated emission. Right, and we could also include spontaneous emission. From 2 to 1. So tau sp is the spontaneous emission lifetime of level 2. So typically it's about 10 milliseconds, the lifetime of this second one. Okay, so in steady state, basically the time dependence of this atomic population goes away. In steady state, we reach some constant population in N1 and N2. Okay, so basically, just as soon as we turn on the pump laser, there are some dynamics, right? The atomic population changes, but within a short time, like within a few spontaneous emission lifetimes, so you can think of the time scale as within like tens of milliseconds or 100 milliseconds. Basically, there is some steady state setup. Okay, and basically this rate of change is now 0, right? Because the pump intensity is constant, right? It's not. So we are sending a CW pump, imagine, and signal. So there is no time dependence in these intensities. So the eventually it reaches steady state. So if we put this equation equal to 0, then you can see that we can get an expression for N2 by N1, right? All other quantities are sort of constants of the pump and signal intensity. So we can get, so we have one equation already for N1 and N2 from here. And then from this equal to 0, we have another equation in N1 and N2. So we can find the steady state population N1. Okay, so from here, so from the steady state condition, we get okay, so the fraction of atoms in pump to the second level as compared to the first level depends on both the pump intensity and the signal intensity. Okay, so I put a tilde here. So this tilde basically denotes that this is a normalized intensity. So the intensity divided by some constant. Okay, and you can check this constant is basically okay, so this is some constant intensity which depends on material parameters. Right, so this is the photon energy at the signal wavelength, the absorption cross section. So this is energy per area per time. Right, so it's an intensity. So just from the atomic constants, there is some intensity we find here, which is what the actual intensity is normalized to. Similarly for the pump. Okay, this IP0 is now the photon energy at the pump divided by the absorption capacity at the pump divided by this one. Okay, so now we have this relation N2 by N1, right? Which in general depends on both the radial coordinate and the longitudinal coordinate, because this intensity also depends on both. And we have this equation here, right? So using this and this, now we can find the actual expressions for N2 and N1 in terms of N0. Okay, so we get these. Expression for the steady state population distributions. So you can see that N2, the number of atoms come to this excited state scales with the pump intensity, right? But in some non-linear fashion, and that is also dependent on the signal intensity. Whereas the population in the ground state, right, that increases again with signal intensity, right? That's due to basically stimulated emission. Right? As the signal intensity increases, it causes more stimulated emission, so the population is one. Okay? So there is some balance going on, right? So for recall that for gain, we wanted the difference between N2 and N1 to be large for large scale, but once you set up this population difference, you have stimulated emission, which sort of counters that the population inversion due to pump absorption, right, and repumps atoms back to the ground state. So as the signal intensity increases, you can imagine that it won't increase forever, right? As the signal power increases along the fiber, it will cause more and more stimulated emissions, which will decrease the population inversion, and the effective gain will go down. Okay, so that is known as gain saturation. We'll see a little bit more about that. So now for amplification, because the condition was so the condition for amplification was this theta times N2 minus N1 should be greater than 0, right? So this is the population inversion condition. Theta was the ratio of the emission to the absorption cross section. Right, so now we can put the expressions for N2 and N1 from here, right, and then we can get a condition in terms of the intensity of the pump, for example. Okay, so we get this condition. So for this to be greater than 0, basically the numerator has to be greater than 0. So you can see, if I put this expression for IIT Taylor, that just means that the pump intensity has to be greater than a particular value. Okay, which depends on this intensity constant that we define in terms of the atomic constant, and divided by this ratio of the emission to absorption cross section. Okay, so if I put the values here. Okay, so this you can see is some threshold pump intensity. Right, so if my pump intensity exceeds this particular value, then I will get gain for the signal. Okay, and now so again, in general, the pump intensity will be a function of the radial coordinate because of the mode profile, and the longitudinal coordinate because, as you know, as the pump travels, it is actually getting absorbed, right? So the pump intensity is not constant with propagation, right? So this gain condition might be satisfied in some parts of the fiber, but not in other parts, right? In general, you can see that you will satisfy this in the initial part of the fiber when we launch the pump power at the input, so that some high pump power, but as it propagates, the pump power goes down, and then eventually after some length, it will go down below this critical value and you won't get gain anymore. So this threshold pump intensity you can see is inversely proportional to the pump cross section absorption, right? So that tells you how strong the pump is absorbed. Larger this number, the smaller the pump intensity, right? So the smaller pump power you need to get gain. Similarly, it's inversely proportional to this lifetime of this metastable state here. So again, higher that value, smaller the pump intensity. So the longer it stays here, the lower pump power you need for gain. So for erbium in glass, this is about 10 milliseconds, as you say. And this it also depends on this ratio of the emission to absorption cross section at the signal width. Again, if that number is high, if the emission cross section is higher, you will get gain at a lower pump intensity. So you can look at some typical numbers. Right, so one thing to note, as I said, this is the pump intensity is a function of position. Right, so now if I look at the cross section of the fiber here, if I look at the core, again, so this is the core radius. Right, I have some doping of the erbium atoms here. The pump intensity profile looks like that. Right, so this is some threshold pump intensity, some constant number. So if I define that, this is the radial coordinate, right? So this is the threshold pump intensity, right? And my launched pump power is such that you can see that, so in this part, near the center of the core, it exceeds the threshold pump intensity. So in this region, up to some radius R0, right, you'll have population inversion again. But beyond R0, the intensity is lower than the threshold, so you won't have gain in this region. Okay, so you can see the higher my pump power, this closer the R naught will be to the core radius. Right? As I increase my pump power, this goes up higher and higher. So the region over which IP is greater than IP threshold covers more and more of the core. Okay, so let's look at some typical numbers. So for EDFA pump with 980 nanometer laser, this absorption cross section is about 3 times 10 to the minus 25 meters square. Spontaneous emission lifetime is about 12 milliseconds. Okay, so if you put these numbers here, so eta is some number close to 1, let's say between 1 and 2, okay, for depending on the signal, exact signal wavelength. So this IP naught is about 5 times 10 to the 7 watt per meter square. Okay, so at first hand it looks like a very big number, 10 to the 7 watt per meter square. But remember that the core is actually very small. Right? The core radius we are talking about is a few microns. So the core area typically, let's say, is tens of microns square. Right? So that's like 10 to the minus 10, 10 to the minus 11 meter square. So in terms of power that you require, it's actually quite small in milliwatts. Okay, so now depending on the signal wavelength, so let's say if I have a signal wavelength of 1536, at this wavelength, this ratio of the emission to absorption cross section is close to 1. Okay, so this implies that the threshold pump intensity is just IP naught. So I move to slightly longer wavelength, let's say 1550. So recall last class we discussed how the absorption and emission cross section varied with wavelength, right? And for longer wavelengths, the emission cross section became higher than the absorption. So this eta is 1.34 for 1550. So the threshold intensity is lower. Okay, so 4 times 10 to the 7. So I go to even longer wavelength, 1580. This eta is now about 1.7. Right, so you can see that the higher wavelengths will experience gain first because the threshold intensity is lower. Right? Okay, so this is at some particular position here. You can see that at some particular Z, there will be some fraction of the core in which gain is occurring, right? And in the rest of the portion there is no gain because the intensity is lower. So, and this will vary as we vary the Z coordinate, right? Because the pump intensity and signal intensity both are varying along Z. So let's see how we can estimate the variation of the pump and signal powers with propagation, right? So that's our final goal because we want to amplify the signal, right? So we want to see how much gain we can get, etc., for a given pump power. Now recall that we could write the equation for the intensity right? So again, in the last class, we assumed a small volume element, right? And we calculated the number of absorptions and emissions in that volume element, which will change to lead to a change in the intensity entering versus leaving that volume element, right? So we can write the rate of change of intensity from the last class like this, right? So again, the rate of change of pump intensity depends on pump cross section, number of atoms in one, right? Because so the pump is getting absorbed from 1 to 3, right? So the pump intensity goes down. There's a negative sign proportional to absorption cross section from 1 to 2 and the number of atoms in 1. Right, so that's the equation for the pump. For the signal, now we have both emission and absorption, right? So because there are atoms in 1 and 2, the signal photon can be either absorbed or emitted, right, from 1 to 2 or 2 to 1. So we have two terms here. So this first term corresponds to the emission, sigma S E times N2. The second term corresponds to absorption, right, minus sigma S A times N1. Okay. So recall we just erased that, but we had expressions for this N1 and N2 as a function of R and Z in terms of IP and IZ. Okay. So basically we can replace those expressions and write this entire equation in terms of just the intensity. Right. So, and the solution of those will give me how the pump and signal intensity is varying. Okay. So these are nonlinear equations, nonlinear differential equations, right? Because N1 and N2 were complicated expressions of IP and IS. Okay. So in general, if you have to solve, you have to take the mode profile, right? So the intensity profile is the pump power. So the intensity profile at distance Z is the pump power at distance Z times the mode profile, which depends on the radial coordinate. Right, so this will be, for example, for the LP01 mode, it will be some J0, right, in the core, which can be approximated as a Gaussian. Right, similarly for signal, so both pump signal, I can write the power at that distance times the mode profile at the pump and signal, right? So this is, for example, the LP01 mode profile. Right, and this F, the mode profile is normalized such that basically if I integrate the intensity over the cross-sectional area, I should get power, right? Intensity times area should give me power. So, I mean, just from units here, you can see that F has units of 1 over area, right? Because this is intensity, this is power. So this is normalized such that if I integrate over the cross section, so R goes from 0 to infinity. So I'm taking cylindrical coordinates, right? So R and phi across the fiber core. If I integrate the intensity across the fiber core, then this should just be the power. So if I plug this in, you can see that basically the condition is, so there is no phi dependence for the fundamental mode, right? So that integral is just 2 pi. So they are normalized such that this integral is 1. Okay, so for example, we can take a Gaussian approximation for the fundamental mode profile, which means that, so this I can write as right. So this function I can write as some e to the minus r square by capital omega square, where capital omega is the spot size, right? We call it this Gaussian approximation. The spot size depending on, for example, the V number at that wavelength, right? So for the pump and signal, since there are different wavelengths, the spot size will be different, right? And for the normalization, I have one over the mode area. Okay, so omega p is the spot size depends on V number at the pump and the signal. Right, so we had approximate expressions for the spot size in terms of V number, for example. So okay, so you can see, so you can solve these equations under the Gaussian approximation. Take this as far as e to the minus r square by capital omega square, right? And so then plug this in, and then replace N1 and N2 also in terms of IP and IS. Okay, so then we get equations which both depend on R and Z. Okay, because there is R dependence here also. So the equations become a bit complicated. Okay, and we won't go through the entire exercise here. If you are interested, you can look at the book. How to solve under this Gaussian approximation for the mode. What we'll do is an even simpler approximation. Okay, because that captures most of the features of the EDFA that we are interested in, and it's much simpler. So the approximation we'll make is that we'll say actually there is no intensity profile with radial distance. Actually, the intensity is constant in the core. Okay, so we'll take like a mode profile which just looks like a constant in the core. Okay, so of course this is a big approximation, right? But the qualitative features that you get are the same, right? Like how the pump and signal power varies with wavelength. The main features you can still capture with this approximation. Of course, the exact numbers will be slightly varying from this exact mode profile. Okay, so what we do is known as the plane wave. Okay, so this one is the Gaussian. So what we'll do is known as the plane wave approximation. And basically, as I said, so we assume that the intensity of the pump and signal is actually just constant across the core. Okay, so now here you can see that the intensity would just be the power divided by the area of the core. Okay, so for the core region, and then 0 in the cladding. So again, basically this intensity profile is just like a constant step here. Right, and the power in this pump and signal will give me the height of this. Okay, so now if we substitute this approximation for the intensity, you can see that now IP just depends on Z because this is now a constant. There is no R dependence, right? So if we plug in this expression for IP and IS here, we can see we'll get basically the same equations. This constant will cancel out, and the same equation in terms of the power instead of the intensity. Right. So yeah. So we end up with these equations for the pump and signal powers, which now only depend on Z. Right? And now we can use the expressions for N1 and N2 that we had in terms of what we call right, and then this eta times N2 minus N1. Okay, so you can see that if I plug in N1 and eta N2 minus N1 here, the equations still look quite complicated, right? We can make some further approximations to sort of get some qualitative feel for what's going on. Okay, so we use what is known as a small signal approximation. So the first approximation was this plate wave approximation. The second approximation is the small signal approximation, basically which assumes that the signal is very small, right? As the name suggests. So recall we want to amplify the signal, right? So for example, you have some optical signal traveling in some fiber over long distances, right? And once it becomes very small in power, then you have to amplify it. Okay. So the signal powers will be typically very small, and pump powers will be high, right? So this approximation basically is that this IS tilde is much less than 1. Okay, recall this IS tilde was IS over IS naught. Right, so if I multiply by the core area on both sides, and this I use the expression so this is the signal power PS, right? And this whole thing I can write as some, so if I multiply with the pi a square, so this thing I can write as some PS naught, right? So again, it depends on just the atomic constants of erbium in glass and then the core area. Okay, so basically a small signal approximation is that the signal powers in the fiber are smaller than this PS naught. So if you again put typical numbers for EDFA, typical EDFA, right? So we know again, so signal wavelengths are in the 1530 to 15 or 1600 range, right? Absorption cross section is sorted to minus 25 meters square. This lifetime about 10 milliseconds. Eta is in the 1 to 2 range. Right? Core size typically few microns, just let's say from 2 to 5 microns in that range. If you put the numbers, this PS naught comes out to be about a milliwatt. Okay. So basically, the approximation we are making is that the signal powers are less than a milliwatt. Okay. So typically, like the input signal powers would be like a microwatt. Okay, in that sort of range, and the pump powers would be in the few milliwatts to tens of milliwatts. For high power EDFAs, they can even go up to like watt. Okay. But once the signal gets amplified and if the signal power goes beyond this value, then we can't use a small signal approximation. We have to use the entire equation. Okay. But we can get some features about the amplifier using the small signal approximation. Right. So basically, in this equation for N1, we just neglect IS tilde. Okay, so the numerator just becomes 1, the denominator just becomes 1 plus IP tilde. So the equation for the pump power simplifies a lot and right, again this PP tilde is P sub P divided by P sub P naught, right, again which was defined. So this is pump power divided by this constant PP naught, which was again this IP naught, photon energy divided by absorption cross section times lifetime times the core area. Okay. And PP naught also has values similar to PS naught. Okay, maybe a few milliwatts. Okay, so this is the equation for the pump. Right, it just depends on the pump. In the small signal approximation, right, the pump power propagation just depends on itself. It doesn't depend on signal power. And then again for the signal, in this expression eta n2 minus n1, we'll neglect IS. So this becomes Okay, and now so for the signal propagation, we can see that, of course, its propagation depends on the pump power. Right? It depends on the signal power, on its own power, but also depends on the pump power. Right? So, for example, if this coefficient is positive, right, that's the condition for gain. Right? So, if this quantity is positive, then you can see that dPs by dz is a positive quantity. So, the gain signal gets amplified. Right? Signal power increases as alpha. But you can see that these are non-linear differential equations, right? Not you can't straightforwardly just solve them to get analytical expressions, right? Even after these approximations, the expressions are much simpler, but still they're non-linear. So, yeah, maybe. And so in the next class, we'll take certain limits of these equations and see the behavior in those limits, which will give us like a conceptual idea of how the powers are varying as the pump and signal are propagated. Okay. But for if you want exact variations, then you have to solve these equations numerically. But yeah, we'll see in certain limits how the behavior looks like, and we'll discuss some properties of EDFAs, gain, saturation, bandwidth, and noise, etc. in the next class.